Fajan's rule. The covalent character can be noticed in ionic bonding. So that can be explained based on this Fajan's rule. So it is called the partial covalent behavior or covalent character of ionic bonds. According to this rule, small size of cation, that is rule number one. And second rule is large size of anion. Now let us discuss this. Small size of cation means small sized cations because of their high electron density. So the small size cations will have high electron density. So it causes to distort. Distort means disturb or or polarize the electron cloud of anion to a greater extent, to a greater extent. So the compounds containing small cations will have more covalency. So smaller the size of the cation, smaller the size of the cation will have the more ionic character, more not ionic, more covalent character in ionic. For example, let me consider lithium chloride, LiCl. This is more covalent than NaCl and KCl. Why? Because of the size of lithium cation compared to the size of sodium and potassium. Then, large size of anion. So, larger the size of anion, larger the size of the anion, greater is the polarizability. Greater is the polarizability. Because in case of larger anion, the hold on the electron cloud by the nucleus decreases. hold on the electron, cloud by the nucleus. So that decreases. Bigger the size, it goes out of control of the nucleus. And because of this fact, the covalent character of lithium halides is in this order. For example, lithium iodide is more covalent than lithium bromide, that is more covalent than lithium chloride, and that is more covalent than lithium fluoride. So everywhere you can find lithium of same size. We already discussed the smaller size of the cation, the larger will be the covalent character, more covalent character. In this case, the same lithium, but they are combined with a different anion of different sizes. So larger the size of the anion means what? There will be more polarizability, and hence the hold of the electron cloud by the nucleus decreases. So because of this fact, covalent character changes in this way. So here, this is more, okay? So it means it increases the covalency. So in both the cases, there are more covalency because of smaller size of the cation and larger size of the anion. So don't forget these two. And that is why this reflects on the melting point also, because we already seen that when the ionic behavior is more melting point will be there. So in this case, this is more covalent. So you can anticipate the melting point less. So in this case, it is 446 degrees Celsius, and this is 547 degrees Celsius. This is 613 degrees Celsius. So 870 degrees Celsius. You know very well that is a higher the ionic behavior, greater will be the melting point. Similarly, lower the ionic means what? Higher the, what is it? Covalency. Lower will be the melting point. So don't forget this concept. Okay. Now the third one, high charge of the cation or anion. So that is also responsible for such kind of, that is partial character. High charge on the cation. High charge on the cation or anion. Let us consider the sodium chloride, magnesium chloride, aluminum chloride. What are the molecular formula? Sodium chloride, NaCl. Then magnesium chloride, MgCl2. Aluminum chloride, AlCl3. Now, what about the sodium ion here? Na plus. Magnesium ion, Mg2 plus. Aluminum ion, cation, Al3 plus. So there is an increase in the charge, right? So higher the charge, higher the charge on the cation, greater is the polarizing power. Greater is the polarizing power because the cation attracts the electron cloud, right? Suppose the charge of the cation is more means what? Its attracting power will be more towards the electron cloud. Hence, there is an increase in the covalent character. Therefore, the covalent character, order of covalent character will be sodium chloride is less than magnesium chloride. Magnesium chloride is less than aluminum chloride. So here it has got single plus, here 2 plus, here 3 plus. Okay. Similarly, greater the charge of anion, there will be more polarizing power. They get polarized immediately. So it is irrespective of the size of the cation or anion. So in this case, we talk about only the charge. In the previous case, we talked about the size of the cation and the anion. So smaller the cation, bigger the anion, more will be the covalent behavior. In this case, higher the charge of the cation or anion, more will be the covalent behavior. Got it? Now let us move to the next one, that is electronic configuration of the cation. Electronic configuration of the cation. Let me consider the cations, two cations having the same size and charge. Then one with some pseudo noble configuration, means that is 18 electrons in the outermost shell. It has greater polarization, that is polarizing power, as compared to the other one with noble gas configuration, that is with 8 electron system. When I say pseudo noble gas configuration is 18 electron system, noble gas configuration means 8 electron system in the outermost shell. Okay, take down. So in this case, we consider that is two cations. They have same size and then same charge, but we need to justify the covalent behavior in such type of cations, because in the previous case, that is the size is different, means based on the size we can judge whether it is covalent or not, and based on the charge we can decide. But when both are of same size and same charge, we need additional parameter, and which is reliable, in this case electronic configuration. In this electronic configuration, we have got two types of configuration. One is pseudo means false, pseudo noble gas configuration. So this means 18 electrons in the outermost shell, right? Then noble gas configuration. So here 8 electron system in the outermost shell. So in that case, the pseudo noble gas configuration with the 18 electron system will have more ionizing power. Okay, that is more polarizability, greater polarizing power. You can call it greater polarizing power. So shall we have a mind map? So what is Fajan's rule? One is based on what? Size. Another is based on what? Charge. Third one is based on what? Electronic configuration. Now tell me that is, let us split like cation, anion. Okay. And this is also cation, anion. Okay. Now in this case, we talk about the same size, same charged cations. So here let us split. This one is 18 electron system. This is 8 electron system. And here the cation. And here anion. Okay. And here also cation, anion. So in this case of cation, what should be the size? Smaller. Okay. And what about anion? Larger. And what about the size? Greater or larger, you can say. Here also larger. Okay. And then here, suppose both of them have same size. Then in that case, 18 electrons has larger. I mean, that is more covalent behavior. Why? In all these cases, more polarizing power. Yeah. So here also more polarizing power and hence more, what is that? Covalency. And here tell me, larger the size, I mean charge, larger the charge, don't forget. So this is regarding size and this is regarding charge. So you should not get confused between these two. So in this case, both of them are larger charge. Okay. So here also high polarism power and then high covalent behavior. Here high polarizing power and then high, what is that? Covalency. And here also high polarizing power, high covalency. Got it? Okay, so don't forget this. Right. Now let us move to the next aspect, coordinate bond. Now let us consider ammonia, NH3, combines with HCl. Actually, it gives NH3 HCl. This is ammonia. This is hydrogen chloride. So this is ammonia hydrogen chloride. but we say NH4 plus Cl minus, ammonium chloride. Why? Let me explain. So nitrogen, it has got a lone pair of electrons with the trigonal structure, pyramidal structure like this, H, 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 and this is the lone pair of electrons, and it combines with the HCl. The H has got only one electron, and that is gripped by the chlorine already. So it wants to combine with this. In that case, this pair of electron is donated to hydrogen so that it will form a coordinate bond. So this is the donor. Okay. So nitrogen is the donor atom, and here it is the acceptor, right? So a pair of electron is donated, and that is indicated by arrow mark like this. Okay. So we call it, that is hydrogen. Since it has donated its own electron, it becomes plus, and this is H, 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 and this is Cl minus. So that is why we call it ammonium. This IUM represents the cationic nature of ammonia. Then chloride. Okay. So the overall is, this is plus, and this is reflected as NH4 plus. And similarly, we can build up other examples also. You can go through your textbooks also for various structures like sulfur trioxide, take down SO2, O3, ozone, hydronium ion, H3O plus. Then you've got this NO3 minus, nitrate anion, and nitric acid, HNO3. So this will be your worksheet. Okay. So develop the structure like this, indicating the donation of the pair of electrons. So please go through the book and do it. Next. And for which is useful for to decide this kind of bonding, you can work out the Lewis structure. Okay. So based on the Lewis structure, you can arrive at easily. Huh? That is, the H has accepted this, and that is why this is the acceptor. This is the acceptor, and this is the donor. Okay, and that is why we have developed the bond here, and that is called coordinate bond. Coordinate bond. Okay, that is indicated by the arrow. Next, what are the conditions for the formation of coordinate bond? Definitely you should have a lone pair of electron. The donor should have lone pair of electron. The acceptor must have some empty orbital. So then only it can be donated. Okay, take down. Conditions. Conditions for the formation of coordinate bond. What is the other name for coordinate bond? Tell me. Is also called deity bond. Okay, or donor acceptor bond. So here the first condition is the donor atom should have lone pair of electrons to donate. And what about the acceptor atom? The acceptor atom must contain at least one empty orbital. At least one empty orbital. What are the characteristics of coordinate bond? What are the characteristics of coordinate bond? Point number one. They are usually insoluble in water. They are usually insoluble in water, but soluble in organic solvent. Organic solvent. It means they are insoluble in polar solvent. They are soluble in non-polar solvent. Okay. Next, the melting point and the boiling point of these coordinate compounds are usually higher than that of coordinate compounds, higher than that of the melting point and the boiling point of the respective covalent compounds. They are pure covalent compounds. Then, as far as electricity conductors, they are bad electric conductors, insulators, you can say. They don't conduct. Next point. The coordinate bond is generally rigid and directional. The coordinate bond is generally rigid and directional. It means that they move towards, directed towards the acceptor, go not to acceptor. So they are directional. Hence, they show isomerism. Isomerism means the molecular formula will be same, but that structurally they are different. So that is because of the different orientation. Let us consider the formation of oxyacids of chlorine. So chlorine forms four types of oxyacids: HClO, HClO2, HClO3, HClO4. So what is the first name? This is oxyacids. Can you name the first compound? It is called hypochlorous acid. And this is chlorous acid. You just know only hydrochloric acid, but these are called oxy acids of chlorine. So chlorous acid, and this is known as chloric acid, not hydrochloric, chloric acid, and this is known as perchloric acid. Note down HCl, that is hydrochloric acid, is not oxy acid. Is it not? Because there is no oxygen. So you do not get confused with it. So all these acids contain one OH attached to the central atom. Okay. So the hypochlorous acid is a covalent compound that and possesses no coordinate linkage. No, take down. Hypochlorous acid, it has no coordinate linkage. So it is not a coordinate compound and it is a covalent compound. Okay, take down. So it is a covalent compound. Whereas the remaining, it has got one covalent linkage, coordinate linkage. I can say one Cl, coordinate linkage. Here 2 Cl, here 3 Cl. Let me explain. Now let us talk about the chlorous acid, chloric acid, HClO2. So what are the acid we have discussed so far? What is this? HClO, hypochlorous acid. What is this? Chlorous acid. This one HClO3, chloric acid, and this one is perchloric acid. Okay. Now let us see this formation of chloric acid. And before that, let us draw the structure. Um, First, let me take HClO2. Coordinate link means that a pair of electron is donated to from the donor to acceptor. I'm trying to explain. Please wait. Now you have the central chlorine atom. Take down central chlorine atom and put the oxygen here. Follow me closely. Then another oxygen, and that is tied up with the hydrogen. Okay. Now tell me the electronic configuration of hydrogen. How many electrons are there in the hydrogen? Only one. Okay, so I can put one. And what about oxygen? How many oxygens are there? How many electrons are there in the outermost shell of oxygen? Six. Let us count. Two, four, five, six. And let me consider the chlorine with the cross mark. So how many chlorine electrons are there? Tell me. Seven. Seven. So how many? How many electrons are there in chlorine in the outermost side? Seven. So one, two, and then three, four. Then you have five, six, then seventh one can be here. And what about oxygen? Let us put the dot marks. How many oxygen electrons are for oxygen? Tell me. Six, two, four, six. Okay. So now you guess from which atom to which atom the coordinate bond will happen. Very good. Okay. So it means this is the coordinated electron. Okay. Because that is donated to oxygen. So you can write down like this. H. Okay. So this is a pair of electrons. So one bond. And what about this oxygen? And this is involved with one bond. Okay. Then what about this chlorine? Right? Then that is donated to oxygen. That's it. Okay. We understand now. If you want, you can have the electron top also. So here, two, four. Here, two, four. And a pair of electron is donated by the chlorine. And here, oxygen, two, four, six. Okay. Now, can you do similarly for the next one? HClO3, right? So this is HClO2. Now let us try HClO3. Tell me, let me draw. HClO3, let us draw the skeleton. Cl, okay? That is the central atom. And here, oxygen, do it carefully. And here, you must have, in all these cases, OH is there, okay? So take one oxygen and one hydrogen, right? Okay? And we need to put one more O because it's HClO3. So let us put O here. You know very well there is one OH attached to chlorine. The remaining two oxygen is that they are attached to chlorine, right? Now shall we attempt to draw the and you know very well that is um, okay. Let us put oxygen, hydrogen electron like this, and oxygen electron. So two, three, five. Do it carefully. Six. Okay. Now what about chlorine? 2, right? And then 4, okay? And then 6, 7, right? Now, what about oxygen? 2, and then 4, here, 6. Now, can you tell me here? Tell me 2, 4, 6. Okay. In both the cases, oxygen, two oxygens are acceptors here. It means now it is going to travel where? So the donation happens here. Are you able to follow? And here. So it means I hope now you should be able to understand that it has got two coordinate linkages. Got it? So shall we draw? H. You have to draw both. Okay. H, O, and then bond. I'm going very slowly because you have to understand the concept. Then here one coordinate bond O, another coordinate link O, and that's why I said there are two Cl. I hope now you should be able to understand this, right? Okay. Now let us try to put the dot formula for oxygen 2, 4, 5, 6. Done. And what about this chlorine? 2 and 4, 6, then 1, 7. Okay, it is there. Then 2, 4, 6. 2, 4, 6. Got it? Sure. Can you do similarly for the perchloric acid? Can you try? You're done. Very good. You are genius, really. You are fit to be a chemist. What about Shanvi? Shanvi, she has gone out of camera, right? Oh, have you done that? The third one? Okay, let us try. So how to, you can explain, Prusha. You tell me, you guide me, let me draw. First you put the central atom, Cl. So what is the molecule we are going to discuss? What is the name? Perchloric acid. What is the formula? HClO4. What I said? There are how many Cl links? Three. Okay. Louder, please. It is getting recorded. Ah. Now tell me. Okay. H. This side. O. O. And above also. Yeah. Tell me now. Shall we draw the bond? Shall we draw the bond directly so that you can easily understand? OH, right? And OCl, right? And simply put, that's all. Finished. Okay. Now we can draw the dot formula. Can you? Shall we try? Tell me H, one bond, O, and Cl. Then you got already O and O and O. Now tell me the electron dots, the pairs. How many pairs are there in the left O? What are them? Two. And what about the top? Three pairs here. Yes, that's so. Okay, got it? Are you able to follow? Can you show me the formation of coordinate bond in ozone? Try. Ozone formula O3. Okay, I will give you a simple structural one. You have to draw the electron dot. So that will be easier. Now tell me. O with how many electron dot? Left to O. How many electrons? Two. Central one? No, one pair. How two? Here, oxygen. Very good. Very good. Okay. Now, shall we try ammonia? Ammonium, right? Okay. So, what is ammonia? NH3 only. So, N, and you got hydrogen, 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 and with a lone pair of. Now, one H plus is going to add. So, which is the acceptor? A is H plus is the acceptor. Which is the donor? N is the donor, right? And it is going to donate one electron to H plus, right? So that it becomes what? N, H, H, and then H. Now a pair is donated, is it not? H. So this is donated, okay? Right? So that it has lost one electron now. So it becomes NH4 plus. So you can write this as N H H. Sorry, N H H H H. So one coordinated form and put plus as a resultant. Okay. Shall we try formation of hydronium ion from water? Try that. Take water, add H plus, and form the structure of hydronium ion. Do it. Formation of hydronium ion. What is the formula of hydronium ion? Shall we? It can also be called a dash. Anyone? Protonated water. Protonated water can also be called acidulated water. When you take some acid and drop it in water, then it becomes hydronium ion, protonated water. Okay. So hydronium ion. Ah, good. Lightning fast. Okay. So formation, tell me now. Oxygen, H2O, is it not? So let us put hydrogen, hydrogen like this. And here OH bond, and here also OH bond. Now you've got two pairs of electron, right? Oxygen. And one H plus is going to combine. So a pair of electron is going to be donated here. So it becomes what? So this is donated. So it becomes O, H, H, and then H. Now it is donated. So it becomes plus here. So you can call it hydronium ion. That is O, H, H bond. Okay, coordinate bond H. Remember. So the resultant is hydronium ion. Okay. Shall we try nitric acid? Do it. Nitric acid. Formation of nitric acid. HNO3. Let me draw the bond structure. H, O, and then N, O, coordinate, double bond O. I have given the clue. Now you have put the electron top. So H bonded electron with the O, and then bonded electron with the nitrogen, and then the nitrogen has donated a pair of electrons to oxygen, and you have got here that is two pairs of electrons that develops double bond O. Got it? Okay. Now let me recap the entire compounds. That is comparison. This is a very frequently asked question. Okay, take down. Comparison of ionic, covalent, and coordinate compounds. Ionic, covalent, and coordinate compounds. So let us go ahead with the properties in the first column and ionic in the second column, covalent in the third column, then coordinate in the fourth column. Now let me list out the properties. Binding force. Second, melting point or boiling point. Third, conduction. Fourth, solubility. Solubility in polar solvent like water. Then solubility in non-polar solvents, in organic solvents. Non-polar solvents like organic, for example, let us consider ether. And finally, physical state. Now let us proceed one by one. Now the binding force in the case of ionic, what are the species which are responsible for this binding force? And let us talk about the strength also. So in the case of ions, it occurs between ions, right? Take down between ions. And what about this covalency between molecules, right? And what about coordinate? This is in between. For example, in this case, strong Coulombic force will be there, right? So strong Coulombic force of attraction. So immediately you can anticipate high melting point and boiling point. Okay. And as far as conductance is considered, concerned, good conductor. Conduction means conduction of electricity. So good conductor in fused state, that is very important. Fused or solution state. And here, what about the strength of the force? Smaller is van der Waals, is weaker, right? And this is in between. Then what about the melting point and boiling point? It is less than ionic. And here also it is in between, in coordinate. And here this is a bad conductor. Okay. And here, however, it is better than covalent. And the solubility in the case of ionic compound is in water high, in organic solvent low. Whereas in covalency, it is low in water and high in organic solvent. Whereas this is in between. Okay. And what about the physical state? Generally, they are solid. Whereas in this case, liquid or gas. Whereas solid, liquid, gas, all are feasible. So I will send some of the important worksheets, try to solve all those things. So with this, we have completed the first part of covalent bonding. So chemical bonding is a very vast topic, and you have got a lot of important aspects to be discussed and memorized, and completely you can anticipate a lot of reasoning questions in chemical bonding. Okay. So we will continue the next class, and I'll be sending some worksheets. So try to complete all those things. And if there is any doubt, you can ask me. I'll try to send the solution. And even after going through the solution, if there is any problem, let us discuss in the subsequent classes. Okay. Right. Bye.